Good morning, everyone. Firstly, I'd like to thank the leadership of the temple for this kind invitation through the force of nature that we know as Jaya to me and JP to some of you. So he's basically convinced us as scientists that we have some contribution to make to spirituality, and this is what I'm hoping to fulfill today. But before I go on, I'd like to acknowledge my past, my present, and my future. My past is my ancestors, those who are not longer with us, who've made the path possible for me to travel through this journey of life. And I also thank my present, my family, who give me the support to travel through this journey, and my friends who are here, who allow me to associate with them so that they can pass on their wisdom to me, and that I can stand on their shoulders to look further than I can on my own. And I also thank the future who are here, the students who are going to carry on the work that we are going to leave behind, hopefully, to make this world a better place. So thank you very much. So the question is, what is spirituality? What are we thinking about? What is going on in our body or in our brain? So how can we answer this question, right? Reading our physical thoughts, we are not telepathic, right? So we understand through experience what somebody else might be thinking, but not accurately. Okay, so how do we know that when we're doing meditation or carrying out some prayers, that what part of the brain or what are we actually thinking about? How can we visualize this activity to better understand how we are perceiving this information? So can we use brain imaging to see our thoughts? Okay? So what is brain imaging technology? So let me start from the real basics. So hopefully I'll take you through a journey that I went through myself on how I reached where I am today. So they started off imaging in the true form that we know today, or some of the aspects of imaging that we use today started in the 1920s, where a psychiatrist was taking EEG measurements for the first time to actually realize that we can measure electrical activity in the brain. Okay? And that basically sparked off, can we understand the brain from there? Okay? So the early EEG was able to detect electrical activities in the brain, and that were rising and falling as the patient was going through various experiences. Okay? And that was basically the cells are communicating with each other and producing this electric activity. Since then, neuroimaging techniques have developed over time, as we understand. So we had a very excellent presentation on quantum physics and physics itself, which is basically the basis of everything that I'm going to be talking about today. So you would probably be thinking, what was Marco talking about? What is the essence of all the physics that we've learned? This is it. This is the cusp of everything that we've learned in physics. So what we can do is use these techniques to understand the neurophysiological and neuropsychological predictors of the normal functioning brain and also the diseased brain. And then how can we manage them if we understand these predictors? So the commonly used brain imaging techniques, so I've just put the list here, and I'll talk about one in particular. So we have functional imaging, computer tomography that we know about as CT, the activities in the brain. So principal benefit of brain imaging, so I've kept this really low, so hopefully that you will be able to stay with this imaging technique. Principles of the brain imaging can easily be performed. That's the critical bit. And it simply involves lying down and being still while we take scans, okay? And then we put the patient or the volunteer through various activities so that we can measure them. Modern brain imaging techniques enable doctors and researchers to map regions and functions of the brain in a non-invasive way. So the reason I put non-invasive in that fact, because PET and SPECT are not non-invasive in the true sense that you have to inject radioactive materials to be able to see what the brain functions are. Whereas the other ones, you just have to lie there and let the scan do the work, and then let the clinicians and the researchers do the interpretation. So fMRI is basically using, so we're all familiar, most of us probably have heard of MRI. And I'm not going through the physics of MRI because each of these slides that I give you is an hour's talk in itself, okay? So you have to take my word that MRI works, okay? So MRI is basically, or fMRI is actually a specialized technique within the MRI community. So we're taking one aspect of MRI and enhancing it so it becomes functional, okay? So it may be possible to see what's going on inside the brain while people are thinking or actually doing some work. So rather than just looking at anatomy, so what is the difference between fMRI? So MRI studies are basically, and we're actually trying to see what the brain structures are like, if we can find a brain, that is, okay? Functional MRI is telling us what are we thinking about, okay? So are we thinking about some sleep or some samosas that we're thinking of, maybe some sweet lassi that we're thinking of, or, you know? So this is basically the difference between the two. MRI is the primary instrument, and fMRI is basically an aspect of it, okay? So what is fMRI in itself? So it was invented in the early 90s. So as somebody basically was working on trying to do different, so MRI basically works on pulsing sequences. So they were working with different types of sequences and to see what information we can gather from the brain that we don't already have. Okay? So basically what they wanted to, initially they just wanted to see whether we can measure blood flow. Okay, so that was the principal period. Can we see a brain functioning and look at blood flow in itself? And then realize that we can actually, blood flow actually relates to something else. And this is what I'm going to tell you about. So MRI can reveal what part of the brain is active during specific functions, like lifting your arm or fingers, tapping, and then basically thinking about something as well. So and I'll explain how we do this particular experiment. Researchers and clinics can use this information to better understand normal brain function or diagnose disease, and then monitor and then treat various conditions. So when you're treating somebody, you want to see whether there's a change in what you've been seeing as pathology. So this is, you're probably familiar with some of these images. So the background in black and white is the MRI image. And what you see in color is the color encoding of the information that we've gathered through fMRI, which I'm going to explain how we get there. So you can see the two techniques are interdependent on each other. So how does an fMRI work? So what do we mean by an area is more active? And this is very important to understand. So please bear with me for a few minutes. So the brain area considered more active when the neurons start firing and sending electrical signals between themselves. And so this is basically, we take a baseline. That means you're not thinking, you're just lying there. And then we ask you to do a particular task and see how which part of the brain starts becoming more active. Okay? In certain brain areas, they're more active when you raise your leg, for example. Obviously, not the whole brain's going to light up. Only certain parts of it are going to light up. And an fMRI indirectly measures electricity. So what we're not doing is we're not measuring neuronal activity in itself, but we're measuring the consequences of neuronal activity because there is a higher metabolic demand in that area. That's very important to understand. So this is not neuronal activity, but increase in blood flow due to neuronal activity. All right? So what happens is that you get more oxygen in the area, and that causes a disturbance in the electrical field, not directly. Again, I will explain that to you. It's not the oxygenation that causes the problem, it's the deoxygenation which is left behind. So this is called it's called the Bold effect, or the Bold response. And it's basically blood oxygen level dependent response. Okay? And I'll explain that to you in a minute. So how does this work? So this is the take-home message. I've simplified it. So the brain is about 2% of the total body weight. This is an approximation, it's not accurate. But it consumes about 20% of your total oxygen levels. Okay? And what that means is the brain is functioning at its full capacity up to 99%. Right? So if you want to measure that little bit more activity than you had before, you've only got a bandwidth of about 0.1 to maximum 5%. So this is a very, very sensitive method. You have to have very sensitive methods to be able to see this. If the brain is working at 99% capacity, and then you're measuring a little bit more of that, it's going to be very difficult. Unlike, and then obviously you can imagine if there's all this blood flow going through there, through the brain, because it's consuming 20% of the oxygen, you can imagine how much blood is flowing through there at any given time. You can measure any changes in a little bit of amount of oxygen is going to be very difficult to measure. Okay? So this is very important to remember. It's not an easy technique where you just lie in there and then you basically gather the information. So basically, you know the blood travels from the arteries to capillary beds to the veins. And then as the neurons become more active, they require more oxygen through the red blood cells. So more red blood cells flowing through there, because in that localized area, and this is very important, in that localized area, the blood vessels open up a little bit, okay, to allow more oxygen to go through the system. So what happens is that the hemoglobin itself, we know from the 1930s, from the work of Mark Spritz and things, that it exists in two forms, diamagnetic and paramagnetic. So deoxyhemoglobin, which is paramagnetic, excuse me, I've got a fly, is basically causes distortion in the magnetic field. So please bear with me. Deoxygenation causes distortion in the magnetic field. So we measure the distortion that's caused by deoxygenation in a normal brain, in a normal resting brain. Then we activate the brain, and this what happens is that the deoxyhemoglobin now starts being diluted by the oxygenated blood which is coming in further on. Okay? So we're not measuring oxygenation, we're measuring deoxygenation level of flowing out. So this is very difficult to explain, but it's easy for me to understand. Okay? So what we're measuring is the loss of signal from deoxyhemoglobin because it's being replaced by oxygen. It's just a dilution effect. So it's a very simple technique, but it's a very powerful technique. So you can imagine in a basal state where we're just resting, we have a basal neural activity, basal cerebral blood flow, then basal levels of deoxyhemoglobin, and a basal MRI signal. Okay? Then oxygenated blood produces fewer disturbances, so the deoxy is going to basically has been the disturbing influence. And that disturbing influence is now going to be decreased. So the longer it's decreased, we assume that more oxygen is being used in its space. Okay? So what happens when you stimulate, you have increased neural activity, increased cerebral blood flow, decrease in deoxyhemoglobin, that means there's loss of signal, and then you basically have increased MRI signal. That's all there is. So you measure the brain before, you measure the brain afterwards, and the difference between them tells you how active the brain may have been. Simple as that, okay? So this is called neurovascular coupling. So you're not measuring neuronal activity, you're measuring vascular activity due to neuronal activity. Hopefully that makes sense? And then what you can do is you then basically take this information that you've gathered and convert it into a color image that you can then interpret. So how do you carry out this MRI? So some of you may have been in MRIs if you've been unfortunate enough. So basically it's like a big vada, all right, or a big donut. It's a very high field magnet. So the magnetic field is about 10 times that of the Earth's magnetic field. So you need this very strong magnet because you're going to see very small subtle changes. So you need a very big magnet to cause the big signal change so you can measure the small amounts. So you basically just lie in there and then you transmit a radio frequency. And this is tuned to proton, to the most abundant molecule in your brain, which is water, which is 90% of the brain is water. So you tune it to the water signal, you pulse the brain with this particular frequency that the water responds to, and it's only for a very short period of time, only 10 to 20 milliseconds. Okay? Then you turn off the transmitter, and then what you're doing, receiving radio waves, you're looking for the echo that comes back. In my brain, you probably get no echo at all, right? So basically, the echo that you're looking for is what the brain response is to that particular signal. So it actually retransmits the radio signal in a slightly different form because of the environment that it's in. Okay, and that's basically what you're measuring in MRI. So then you convert the radio frequency data that you've gathered, which is bounced back from the brain, into imaging data. Okay, so this is, I mean, as I said, each one of these slides is about an hour's talk in itself on how do you acquire this data. But take my word, this is how it's done. So how do we do the fMRI experiment? So unfortunately, the laser doesn't work, but that's fine. So basically you have a magnet on the left-hand side, and the patient lies in the magnet itself. And then you can stimulate the activity in the brain through two different ways, either visual or audio. So you can put headphones on, and then every time the patient or the volunteer hears something that they're meant to, they will press a button. Okay, so you know that when that button is pressed, the volunteer or the patient is hearing that particular noise, and then when you interpret the fMRI, you correlate the two together, then you can see that that particular brain was lighting up when that button was pressed. Okay? Or the other way you can do it is a video projection. Right? So you don't have to have audio, so you can project while you're in the magnet with prisms. So the volunteer is actually looking at a screen in front of him or herself, and then you can transmit various information onto the screen, and when they see the image, again they will press a button, and that will tell the operator when the fMRI would be correlated with that information. Okay, so it's really simple to do the experiment, but it's quite difficult to interpret the data. And this is what you're going to do. So you're basically taking structural images to start with. So you're just taking baseline images. What does the individual brain look like? Right? And then you basically acquire the functional imagings at the bottom, which are very, very crude. But then you put them through a computational method of statistics. So let me explain something else to you, is that it's very important to understand that fMRI is a probabilistic map. What is the probability that that particular brain is lighting up at that particular time? It's not a definitive marker. Okay? So it's a probability because it's very difficult to do this study in individual brains. Okay? So most of the studies that I'm going to show you have taken cohorts of patients and then put all the data together and see whether there is a correlation between all of them to come to a single conclusion. You can do individuals if you already have this data, because then you overlap onto them. But when you're actually doing the first type of studies to understand how the brain is working, you need lots of volunteers. So they can create a unified map, a unified function, and then you can see loss of function or gain of function from an individual based on that map. Okay? So before the fMRI was there, so this was basically created in 1957, so from all the EC data and all the loss of function data, all the pathology data that we had, either through neuropsychiatry, neurosurgery, so we could allocate different functions to different parts of the brain. Okay? So if we know that a particular, in those days, mostly pathology, if that particular part of the brain was affected, you would know there was a loss of function in that particular area. Okay? But since fMRI, just look, so you can imagine how much data we required and how accurate it is, rather than these very big areas that you possibly imagine because of the resolution of the EEG most of the time. So they've created these maps, functional maps as they're called, from a biobank of thousands of people, right? So what they've done is basically taking resting state images and compare them to task-related images. So what they've asked patients to do various tasks and see which areas are lighting up and correlate those areas with a particular brain structure. Okay? So now that we have this map, and now we have the function on top of that, now when we put somebody through a particular task, we can see which part of the brain is lighting up and what that physiological association may be with. Okay? And so this is hopefully, I'm going to try and explain how this work maybe help us to understand what we're here to understand. So it's also very important that we do psychometric analysis, okay, to understand what is the patient or the volunteer actually thinking, right? We ask them to do a particular task, but we also must be sure that they understand what they're meant to be doing in the magnet so that we can then interpret the data. So the first data you can see is basically single patient data. So you basically ask them to draw just a line of how they were feeling when they were put through various exercises. So before the scan is on the left, so the red line is basically the mean. So you can see the variation. So the person at the bottom, he wasn't engaging at all, right? No spirituality at all. Whereas the person at the top, very spiritual. So you can see the difference you have between them. So it's very difficult to understand how the population might be thinking in general. But it's very important to do this. So that's basically how were you feeling at the particular time? They were shown a control video of a cartoon or something and see what they were responding. And then a quotation. So this study was done in a Mormon spiritual study. So all these were Mormon believers, right? So we wanted a homogeneous population that believed in just one particular aspect of a spiritual reading, okay? And then basically prayers. So this is when they prayed themselves. This is an internal praying response. There's no external response at all. This is when they're asked to pray themselves. And then spiritual reading, because they have an audio visual, so they have to read a spiritual reading, and you can see how they were feeling. They obviously got a higher feeling of goodwill, and then obviously other audiovisual responses, and then quotations again. So you keep asking them the same questions after a gap to make sure it's always the same area that's lighting up. You can't just do it once and assume that's the area that's lighting up. You give them a break, give them something else, and then take them back to whatever you wanted to test, and then keep comparing to make sure that it's always the same area that's lining up, okay? So this is what I mean by doing a lot of hard work in the background before you even get to the fMRI. And then basically the bottom is basically they had to tell us how they were feeling according to these 14. So this is basically traces drawn. So after the scan, the participants were selected from 14 terms which commonly address from religious leaders as to which terms best describe their spiritual feeling. For example, there were warnings, prompting, still small voice, whispering of the spirit. So you can see the one that lights up for most of them is feeling a sense of peace, right? Whether they were basically praying or spiritual readings, or have some quotations at them. So you can imagine the red one in the middle is basically where everyone had exactly or almost the same thoughts. Okay? So this is the sort of information you need before you even get to the fMRI. Now when you get to the fMRI, so this is basically a slice through the same area of the brain. This is very important, okay? I'll come back to another aspect. So this is the same area through the midbrain. So the first image, area A, is information gathered from the literature. So when you reward someone or they feel rewarded, that midbrain lights up, as you can see there. Okay, so we want to see whether if you're in a spiritual environment, is it a reward? Do you feel rewarded or not, or is it something else? Okay? And then brain activation associated with feeling the spirit while viewing quotations. So this is basically B. You can see different areas of lighting up. They're not considered reward centers, right? Although you feel rewarded because you have a higher spiritual feeling, it doesn't light up in the same area. And then visual projection. You can see this was another part of the brain lights up when you have scriptural passages either read to you or you read them yourself. And then the brain activity associated with feeling the spirit when viewing quotations. So you can see the first one is having scriptures read to you. The second one is actually viewing them yourself. It's always not the same thing. Okay? But the other thing is there's also a left and right difference as well. So this is the left and right nucleus accumbens activity before and after moments of spiritual feeling. So you can see the brain is pretty complex. So different types of spiritual experiences light up different parts of the brain, right? It's not always the same part. Right? And then what you can do is then you can work through the whole of the brain. So this is taking brain but at different parts. So these are brain slices. Okay? So the first one that the original one I had was basically a single brain image, a single brain slice of a midbrain. So this is now walking your way through the brain to see which, so you can have a wider picture of what's going on. So again, you can see different tasks. So the red, what you see in red is basically readings from quotations from religious leaders. So you can see all the red bits are lighting up. It's very generous. Spiritual scripture readings are only in blue. It's not always the same thing. It's not always the same areas that are lighting up when you're listening to your leaders. Okay? And then prayer, which is an internal activity. So when you're praying, again, different areas there are some common areas, okay, for all three, and there are some areas which are separate to each other. All right? So you can imagine how difficult it is going to be able to understand how we are thinking. So this is from another study. They basically went on to show that spiritual cues relate to neutral, relaxing cues when you compare them, okay, are associated with reduced activation in the inferior parietal lobe. So now we're actually saying that there's reduced activity in a particular part of the brain. The brain region, this particular region, contributes to processing information, attention impulses, control, reasoning, and sensory processing. Very high functions. Okay? And additionally, when you compared with stress conditions, the spirituality condition was associated with reduced activity in the medial thalamus and striatum. Okay? So implication of these studies was that spiritual experience may have profound impacts on people's lives, where imaging has demonstrated that if you're re-experiencing spiritual experiences, activates the brain inferior parietal lobe, and that basically engages the same area that we know controls your impulse control, your higher sensory processing. Compared with stress conditions, rather than re-experiencing spiritual reading, you can see it's associated with a different part of the brain. Okay? So this study may provide some compelling evidence of how brain imaging may be able to help us to understand the neural basis of spiritual experiences. And as the science of spirituality and its relationship to health and behavior are going to change as we move over time, this is becoming more and more complex. Okay? So scientists and spiritual practitioners may be able to use brain imaging to better understand their roles in resilience and recovery from strains and stresses of normal life, using brain imaging and looking at the neurophysiological and neuropsychological markers that we already have information on. Okay? So these results tentatively suggest, remember this is tentative, that foundations for spiritual experiences may be similar across different traditions and practices. So this is very important, that although spirituality may be practiced in different religions, there may be commonalities, and this will be very important to understand. Okay, so what is the commonality of a spiritual, somebody practicing in Buddhism, in Mormonism, in Catholicism, and not any religion at all, but they feel spiritual. Okay? Thank you very much for listening.
Thank you, Professor Kishore Bhakoo. You have proved us how to measure the objective changes in the brain, which we felt till now only in a subjective manner. Thank you.